All right, class, this is the incline plane problem with tension. This is actually problem number 17 on page 117. Now, we've already worked this one in class, and for those who were absent on Friday, this is a rework to get them caught up and familiar with what's going on. So we have a 85 kilogram block on an inclined plane of 30 degrees. We're asked to find the tension of the cord, and if the cord were cut, what would be the resulting acceleration on the block? So the first thing we need to do is we need to draw a diagram. Now, some people prefer to draw their free body diagram on the diagram itself, or make a separate diagram. But the overall preference in class has been to draw it on the diagram itself. So I'm going to give in to popular demand. Okay, so the first thing we want to do is we want to draw a picture of this body, how it's suspended on the incline, and I want to identify the center of mass on this body. Now, the first thing we want to do in our free body diagram, first thing we want to do is identify all external forces acting on our body. And body, we just mean object. So the first thing we need to do is look at all the forces that will act on this body. So we've already talked about the gravitational force, the force that wants to pull the body straight down to the center of the earth, and we say that that is Fg, and Fg is negative mg. Now I say negative mg because our coordinate axis system is like so. We have, don't mean to write there, but I'll need that space somewhere else. This is the plus y, this is the plus x. We consider that our center of mass for our object, and any motion in this direction gives us negative x. Any motion in that direction gives us negative y. So essentially, what we have is this tilted axis system. We have this tilted axis system where our plane is on the x-axis. We utilize what we know about geometry to help us solve these problems a little bit, and it makes it much more simpler than breaking things into many, many different components. So, the force gravity, gravitational force, is one force that's acting on this body. And we have the normal force that's acting on this body. And the normal force pushes straight up. It always goes straight up. And it is the force that this incline exerts on the object which keeps it from breaking through the incline. Now, in the problem, the object is attached to this building or brick by some rope. So anytime we have a rope or cable, we call it force tension. Call it force tension. So now we are pretty far along in solving the problem. The next thing we need to do is to break our forces up into components. So to do that, I like to draw this chart. And we have our force, where we have our X component, and we have our Y component. Now, let's look at the force normal. The force normal is perpendicular to the plane. The force normal is perpendicular to the plane. So force N is perpendicular to the plane of incline. And since it's purely perpendicular to the plane of incline, it will have no X component. Everything of the normal force is completely in Y. So we can write out again and say, you don't have to write this out, but this is for your understanding. Fn has only a Y component and no X component because it only moves in the positive y direction. So for x component, we can put here is 0. And for y component, well, we don't know what the normal force is, so we can just write in Fn. Now, let's look at the force tension. I could draw my little arrows. The force tension. Now, the force tension is completely parallel to the plane of incline. Notice that I said the force tension, not the component of force tension. The force itself is completely parallel to the plane of incline, and therefore there is no y component. Ft only has an x component. So I can come over here and say that force T, well, we don't know what force T is. We wasn't given any information about force T, but we know that since force T is parallel to the plane of incline, it will have no y component. That is very important. Now, let's examine the components of Fg. Components of Fg. So if we look here at Fg, we see that it is neither parallel or perpendicular to our plane of incline. It is neither perpendicular nor parallel. Therefore, we will have components. Isn't that something? We will have components. So I can draw the perpendicular component like that, and I can draw the parallel component like that. Now, what do I mean by perpendicular component and parallel? Well, this component here is perpendicular to our incline. This is perpendicular to our incline. This component here is completely parallel, or I tried to draw it completely parallel to our axis of incline. So I normally like to write Fg parallel is equal to Fx, and that is equal to mg times the cosine. Whoops. Since the x is opposite our angle, that would be mg sine theta. And we were given that the incline was 30 degrees, and that makes this 30 degrees. We talked about that earlier on Monday, how to do the geometry and get these angles. Now, on this side, I have Fg perpendicular, and I say that's equal to Fy, and that is equal to negative mg cosine theta. I want you to be able to get all that in. I ran out of space because of that. But let me see if I can highlight this. Okay. So this is the important piece of breaking down your gravitational force components. Now let's look and see what we have. Well, the x component is equal to what? And that should be a negative because I'm going in the negative direction that way. So that should be negative. I'm going in the negative y direction that way. So our x component is negative mg sine theta. Our y component, we're going down from what we said our established axis was yx. So we're going down in that direction of y. We went down in that direction of x, so that makes these negative. So this would be negative mg cosine theta. Now we have so far resolved every force into its components. Now, let's see if we can solve for the tension on the cord. Let's use Newton's second law and say that the sum of the net x components would equal to the normal force component plus the force tension component plus the gravitational force component, and these are all in the x direction, and that is equal to mass times acceleration. Now notice, as long as there is tension on this block, there is no movement, no motion, therefore there is no acceleration. So acceleration for the block stationary equals 0. And that means m times a equals 0. So we can come back in and we can substitute for ma, we can put in 0. So let's do that. Since we're running out of board space, let's put 0 here. Now, let's say Fn, we know that's in the x direction, we don't have to write that, plus Ft plus Fg, that is equal to 0. Now, let's come along and snatch our components and put them into this equation. So the normal force in the x direction is 0, directly from here. Our force tension is what we don't know, we're trying to solve for. So that's Ft. And our x component of our gravitational force is plus the negative mg sine theta. Okay? And we can set that equal to 0 since the block is not moving. So let's solve for the force tension. Well, that is 0. We don't even have to account for that. And we can say if T is equal to move this to the other side, mg sine theta, and if T is equal to our 85 kilograms times 9.8 meters per second squared times the sine of, what is our angle of incline, 30 degrees. So now if T equals these multiplication operations, and we get Ft is equal to 42.1 newtons, and we can say that that is 42 newtons. Okay, if you have a problem with that, pause the video and let me make this correction in the problem. That should be 8.5. My bad. 8.5. So that would give me 8.5 times 9.8 equal sine of 30 is 1/2 divided by 2. That would be 41.6, and that gives me roughly 42 newtons. Okay, so this is 8.5 kg. All right, now I'm going to erase this. All right, so now let's solve for the normal force. So let's take Newton's second law again and say the sum of F net in the y direction would be equal to the normal force component plus the tension force component plus the gravitational force component, and you know these are all y's in that direction. That is equal to MA but there is no acceleration in the y direction. So ma again equals m times 0, which equals 0. So we can go ahead and put 0 in right here. And instead of rewriting all this, let's just go ahead and take the component form. And I'm going to take the component form from, take these components from what I have in this column. So the component of Fn in the y direction, well, we don't know. That's what we're trying to solve for. So that's Fn. The force tension, since it's completely parallel to the angle of incline, it has no y component, so it's 0. And so now we're back to plus the negative of mg cosine theta as our y component of the gravitational force. And we can set that equal to 0, and we can solve. So Fn is equal to mg cosine theta. And let me do my calculation. Even though we've worked this before. So we have 8.5 times 9.8 and 30 cosine. That gives us a normal force of 72.1, which we can round off to 72 newtons. We can round that off to 72 newtons. So we have found our force tension, and let me come up here somewhere and write down what we found. Our force tension is equal to, that component is 42 newtons. Our normal force is equal to 72 newtons. Put a block around there. All right. Now the last part of the problem, going to erase these pieces. One. Okay. So if the cord is cut, what is the resulting acceleration on the block? If the cord is cut. So if the cord is cut, this force is no longer applicable in our problem. So we can say that what we do know about force tension minus mg sine theta equals a mass times an acceleration in the x direction. We know that much. So we can say that in the absence of this is one way to work the problem, that our block will be accelerating in that direction. That's one way we can work the problem. And we can say a negative 8.5 kilograms times the sine of 30. I could have simplified this by dividing through by my masses, but that's okay, is equal to a mass times an acceleration in the x direction. And that's 8.5 times 9.8 meters per second squared. Don't forget that part. So that should give us the same thing that we got for force tension. And let me be politically correct and put that negative there. And so we get a negative 42 newtons equals, we can put that mass back in of 8.5 kilograms times the acceleration in the x direction. And we can divide both sides by 8.5 kilograms. And that gives us a negative 4.94 meters per second squared. And that is equal to AX. So if the tension is cut, swipe, it accelerates in the negative x direction. That's what that means. At 4.94 meters per second squared. Now, I'm going to erase this part. Let's go back and look at our sum of the x components. Ft minus mg sine theta. And let's say that is equal to ma. Well, I know that when this block was stationary, F FT equaled 42 newtons. I knew when the block was stationary that FT was equal to 42 newtons. So, what I could have done was said that FT, the vector FT, opposes the force that moves the block in the x direction down the ramp. So I could say, since FT equals 42 newtons, I could say that negative F42 newtons would be the force in the x direction that moves the block down the ramp, and I could set that equal to MA, and then I could say negative 42 newtons equals 8.5 kilograms times the acceleration, and then I could divide both sides by 8.5 kilograms. And that would give me the negative meters per second squared, the same as the other way that I worked it. Now, if there are any questions, please ask during class. There will be more videos for PHY 21102. Okay, so if you have any questions or comments, please address those during class in our next meeting.